This is Current Topics in Finance. I'm Andy Kim. We're going to go through chapter 2 of the textbook, which is regression. And then this is lecture note 3. As it turns out, chapter 1, the uncertainty part, is more involved. It requires some prior knowledge about chapter 2, 3, and 4. So we need to go through these 2, 3, and 4 before we go to chapter 1. All right? So please bear with me, and then we're going to go step by step, right? The regression part. The roadmap is this. So I'm going to talk about the 5 assumptions of classical linear regression and something called Gauss-Markov theorem, right? Gauss-Markov theorem. Those 5 assumptions held, then the OLS regression is the best, blue, B-L-U-E, best linear unbiased estimator. So that's the Gauss-Markov theorem, but what are those 5 assumptions? Plus one more assumption, we're going to learn about it as a refresher, okay? For those of you who already learned the regression in your econometrics class, maybe you could skip this one, but this is basic step, right? And then regression through linear models and how to do it in R, and then interaction, factor effects, and design matrices, logistic regression, which is the dependent variable is binary, 0 or 1, like black or white, okay? Kind of right or wrong, bankrupt or healthy company, that kind of things, all right? Estimation. Well, not just the OLS, we're going to refresh our memories, but we're going to talk about something called the maximum likelihood function, and then how about minimum deviance, right? Which is correspondent concept of least squares distance, right? Least squares concept, minimum deviance. And then much of this should be review, but the emphasis will be a bit different. Okay? So, 5 assumptions of classical linear regressions. What are those? Number 1, linearity. Okay, linearity. 선형성, right, in Korean terminology. Those parameters and then the variables, we want it to be a linear combination, right? What is it? Not a quadratic or cubic or sine or rational function or irrational function or whatsoever, right? We work with linear model, okay? Seems like a baby step, right? X times beta plus another X times beta, beta 1, beta 2, blah, 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 okay? Yi should be, okay, Yi, your dependent variable that you're interested in, will be explained by P different variables with P different parameter coefficients, right? Or coefficient parameters, right? All cross multiplication and linear combination like that. Plus epsilon, your error term or disturbance term, okay? We are assuming linear relationship. And y, x, all these things are vectors, right? Vectors, not just a number, but it's the whole column vector. You can think about it, right? And then big X will be your matrix. And then, right, not sine or cosine function or any nonlinear functions, but linear one. Why? Well, it's just a basic step, right? Don't try to overcomplicate it, okay? For example, over here you see sine over whatever square root function, right? Blah, blah, blah. We can call it function of x, right? F of x. No way. Okay, in linear regression, we are playing with the linear structure, right? Non-linear structure, that is what machine learning is about. Okay, you may feel, oh, machine learning, very sexy, but wait for that, right? Let's make our baby step solid enough, right? That's our idea. Now, number 2 assumption, well, there's no perfect collinearity, right? As I said, this is a linear model, right? Linearity assumption. Those of you who are familiar with linear algebra, 선형대수, right? This is basically it, right? Linear algebra. Those linear combinations, right? Well, we want our variables, the column vectors, to be linearly independent, right? Linearly independent, that means one variable or pairs or a group of variables should never be a linear combination of the other variables, any other combination of variables, right? They have to be independent of each other, okay? No perfect collinearity. There's no exact linear relationship among any of the independent variables. No such relationship as, you see xi1 over here in the left hand side. That is for company I, okay? Variable 1, let's say that may be a sales or whatever, okay? Is equal to gamma 2 times, gamma is like some kind of the coefficient, I guess, coefficient for company I's variable number 2. Let's say this is operating profit, okay? Plus gamma 3 times xi, the company I's variable 3. The third variable, what shall we call it? Well, operating expenses, or how about this? x2, let's say x2 is a cost of goods sold, and then this is what? Gross profit. Okay? Gross profit plus cost of goods sold should be what? Sales. Make sense? So sales is nothing but a linear combination of cost of goods sold and gross profit. Okay, gross P, right? Profit. Okay. The gamma, right, could be something similar to 1 or something, right? So it's a linear combination of the other two. Okay, but we don't want the sales and cost of goods sold and gross profit, the three variables, thrown into one regression as a right-hand side variable. Okay, otherwise there will be a multi-collinearity problem, and then there's a problem of redundancy, right? Redundancy, and it screws up your estimation. Okay, this is non-trivial issue. Okay, here is one example. Let's say we are trying to model a company's bankruptcy. Okay, the company's bankruptcy should be your dependent variable. More specifically, the probability of bankruptcy, or should I say, the bankruptcy consequence is just 0, 1 outcome. One is when you are hitting bankruptcy. 0 is when you are non-bankrupt or healthy company, right? So it's a binary variable, which we're going to learn today in logistic regression. Okay, so bankruptcy or not is your dependent variable. Let's say 1 or 0. Okay, and then the reason I say phi over here, big phi stands for, Greek letter for P, probability. So I say phi over here. Okay, phi of bankruptcy, which is like probability of bankruptcy. Why is that the case? Because we are in the spectrum of being more in the financial distress versus not. What's the likelihood? What's the probability of hitting bankruptcy? In the end, we are going to go into this kind of the prediction. Okay, but the outcome variable is 0 or 1. When you throw in the data, it will be 0 or 1. Anyway, that's not an important feature here. But what is important for our discussion here is the bankruptcy. How can we predict bankruptcy, or how is bankruptcy correlated with the company's characteristics or the performance, all these kind of things, so that we could model, we can model company's bankruptcy in a sound manner. Well, the bankruptcy has to do with what? Leverage ratio. If you don't have debt, There's no chance for you to go bankrupt, right? For those companies that do not have any debt, they never go to bankrupt, right? They never go bankrupt. So it's a function of leverage. The more debt, the higher debt you have relative to your asset or whatever you have, right? The more likely you are to hit bankruptcy. So financial leverage has to be one of the explanatory variables. And then intuitively, we know the economic theory says that the beta coefficient over here has to be what? Positive, right? Positive. The theory tells us and predicts us, right? That should never change. Plus, okay, bankruptcy is also a function of your profitability. The less profitable you are, the more trouble you have. Okay, so in recession, or in the kind of economic shock, where your profitability goes to the bottom, your probability of bankruptcy jumps up higher. So we can pretty much predict that this coefficient for profitability, beta 2, has to be minus. Whereas this guy, what did I say? Positive, plus, right? So that's our prediction based on economic theory, okay? And our testing with our data, okay? Testing with our data. What do we have? What do we need to do? Throw in as a right-hand side variable. What do you mean right-hand side variable versus left-hand side variable? Well, left-hand side variable is the dependent variable that goes into your left-hand side of your equation over here. So that's bankruptcy related variable, left-hand side variable. Right-hand side variable is whatever your explanatory variable on this side, okay? Of course, you have epsilon over there. That is just a disturbance term or error term, random error. We're going to ignore that part for now, okay? Anyway, so our economic theory tells this part, and for empirical testing with the data, we need some leverage related variable and one at least, not just at least, we just need one leverage variable and one profitability variable. So for example, debt over asset, yeah, good proxy for your financial leverage, okay, financial distress, right? Should it be the only one that you have to religiously hold on to? The answer is no. Okay, as long as it captures those debt over asset kind of idea or financial distress kind of idea, indebtedness, you're fine as long as you have just one. How about profitability? For example, ROE, return on equity. Do you remember that part? Yeah, net income over book value of equity, right? As long as you have this kind of thing, right? You are happy with that, right? How about profit margin? You can think about it as well. I'm not, I don't say no, okay? But as long as you see this kind of profit coming in, okay? You're fine. That's good. But the thing is, make sure these variables are not redundant against each other, okay? For example, in the last line over here, what do you have? The left-hand side is the same, but the right-hand side, if you look at the first three items, you have debt over asset, debt over sales, and debt over equity. Right? You see the trouble over here. They are highly correlated, extremely highly correlated, and it causes a problem called multi-collinearity. Okay? What the heck? This is the situation you should say, what the heck? All right? And make sure you drop at least two of the variables, please. Okay? And then just play with one over here. Yeah, of course, profitability, you need one. Okay, so I don't say this one ROE, just keep it there. But the other two, right? Debt over sales or debt over equity. If I were you, I would just drop it and run with these two variables, okay? That's what I want to emphasize, okay? The funny thing is, these days, those guys with machine learning, okay, those snake oil salesmen, right, of AI, should I say, okay, they try all kinds of black box model they use where they throw in all variables without even considering this kind of multi-collinearity issue. Okay, for example, okay, they throw in debt over asset, debt over sales, and debt over equity simply because they have it on their matrix. Let's just throw it in and see what best predicts bankruptcy. What's the trouble? Multi-collinearity happens, and then the regression result will be screwy. Okay, if the true relationship, right? I'm not saying the true relationship has to be like this, but let's say the probability of bankruptcy should be 1 times the leverage. Okay, 1 times leverage. Whatever leverage that you have in your variables, right? Then what will happen as long as you throw in all 3 variables like this? All 3 variables thrown in, what kind of coefficients would you see in your estimation? Well, sometimes you may see number 1 popping up for first variable over here. Okay, the coefficient, I mean. Okay, 1 is over here. And the other 0 and 0. Which tells us that the sum of the 3, the leverage, right, is 1. Sometimes you may face that the coefficient for the second variable is 1, whereas the other 2 are 0. In total, it will be 1. Sometimes the last one will be 1, total will be 1, the remaining 2 will be 0. In any of these cases, it's kind of funny in the first place, right? Even more funny is this kind of situation. Well, 1,000 for variable 1's coefficient over here, and then minus 999 for second variable coefficient, and then the third coefficient is 0, and still the total summation will be 1, right? The regression makes it wonderfully into 1 because, you know, the ideal, the parameter, right, the true relation predicted by some model will be like bankruptcy equals 1 times leverage, right? This kind of funny thing can happen in various forms. Like, for example, the last line, for example, minus 198 could happen for beta 1, 99 plus could happen for beta 2, and then plus 100 for beta 3. Okay? You know, all in all, summation will be again 1, right? As long as the summation is 1, the machine will happily throw out whatever number randomly. Okay? Now, what's the takeaway? Okay, what's the takeaway? Well, the machine learning or AI guys, right, the snake oil salesman will say, wow, surprise! Our machine learning found negative relation between bankruptcy and debt over asset or debt over sales by pointing out these 2 results over here, okay? Or 3 results. Okay, you finance guys are doomed. This AI found out a very new relation that reduces your chance of bankruptcy even though you borrow more, which is kind of crazy, right? The economic theory doesn't tell us that. So ML, good luck, or machine, the AI, should I say, right? AI, good luck. So we have to be careful about this multi-collinearity issue. And then third assumptions for classical linear regression. Well, random sampling. Okay, your sample data has to be randomly selected, And then we have a random sample of n observations from the population. It has to be representative of the population, okay? Should not be a selected one, right? A kind of a selection bias could be a serious issue. You have to think about it just like a lab experiment, right? Laboratory experiment. This is why it is better for you to have some kind of physics or biology experiment class in engineering school or the IQA, like a more natural science department in your freshman years, right? If you have this kind of experiment, okay, you'll have some better idea about it. Okay, lab experiment of, for example, COVID-19 vaccine, right? So you're developing a COVID-19 vaccine, and then you have a group of mice over there, right? Mice that you see in the picture, just 2 of them, but let's say a bunch of mice, right? You should randomly pick which mice to give vaccine and which mice to give a placebo, right? Mice should not be able to choose whether to get shot or not. Okay? What do you mean? The mice should not be able to say, yo, doctor, I want that shot. Okay? Which is kind of funny, right? You have to give that completely randomly. Okay? No mice can come up to you and say, I want to have that shot. No. Okay? You just pick up randomly. Your picking should not be based on their characteristics or anything. For example, oh, that one is not white, but it has some kind of spots in it, so I'm going to pick that one. No, it should not be your decision. It has to be just randomly picked up. Random sample, random experiment has to be like that. Okay? And then it goes together with this idea as well. If you don't have that random sampling problem, you will have something of a serious problem called endogeneity. Okay, endogeneity, which means it is the sample selection is determined within the system. Okay, the mice chose themselves. Ugh, that's bad. It has to be exogenous. You experimenter have to be randomly picking up. Okay. Some guys are treated, some guys are not treated. Okay, randomly it has to be picked up. Okay, this endogeneity, selection bias, is one kind of endogeneity bias. Another endogeneity bias is about this kind of things that I'm going to talk about in number 4, exogeneity of explanatory variables. It's called this, right? Exogeneity of explanatory variables. Or the same thing is called this way, zero conditional mean of error terms, right? Your error terms, the disturbance epsilon, okay? Its conditional mean has to be 0. Conditional mean, what do you mean? The x, whatever x value is given, right? Given those information about the x, condition on that, x, the disturbance, whatever is not explained by the regression model, the residual, right? The residual part, right? Given the information of certain x values, right? Those disturbance, those errors, those residuals has to be average 0. Okay? Pictorially, in the picture, you can see it like this. This is one dimension, just univariate regression. One variable x the y regressed on x, just one variable regression. And you see one straight line going up over there. You see it over here, right? And here we throw in, I pick up x1 value, okay? One specific value for x, right? Over there, the regression line, y equals beta 1 times x plus beta 0, tells me, right, the coefficient of the beta is a slope, beta 1 is a slope, and then beta 0 is the intercept, beta 0. But what is important over here is we give a specific value of x, okay, on condition that given value of x1. Your residual, okay, residual should be distributed such that the average will be 0. Right. So zero conditional mean of error terms, right? Epsilon, right? So that's that kind of concept, those disturbance, right? Given the information about those x values, the epsilon has to be 0, okay? But it's easily said than done, right? It's very difficult to see in reality. Your model should be well specified to have this kind of things happen, okay? Models should be well specified. What do you mean? Those x1, x2, x3 variables, right? For example, in bankruptcy, the leverage ratio and profitability, x1 and x2, okay? Is that it? Or do you have some more covariates, which means do you, the true model for bankruptcy, okay, true model for bankruptcy, leverage ratio and profitability, those two variables are they sufficient, or do you have some variables omitted over there? For example, maybe the recession in macroeconomic setting, which is apart from a separate issue from your company's characteristics, right? That macro shock may be another omitted variable that is not incorporated in your model. If that is the case, then based on the two variables, profitability and leverage ratio, your disturbance term, okay, the conditional mean of this will not be 0, and you are in trouble, okay? So that's something called omitted variable bias, and it is causing some kind of endogeneity, okay? And that screw ups your estimate or estimation of your beta, and then t-statistic kind of things. And then measurement error is another issue, okay, that causes problem related to this. This is much more advanced concept that you can discuss later. But measurement error of x, for example, that leverage ratio, okay, should it be book value based leverage ratio or market value based leverage ratio? Okay, shouldn't it reflect the market information up to date? That might be a good idea, but the trouble is market value of debt. How would you estimate that? How would you measure that? The market value of equity, you can measure it using market cap, 시총, right? Market capitalization. But market value of debt, very hard to observe. Okay, what you only have is book value of debt. You're in trouble. The measurement error is there, right? Non-trivial issue. Man, the exogeneity condition, right? This assumption is a very strong assumption that it's troubling everybody. Virtually all the management researchers and corporate finance researchers like me, we face this problem every now and then. You ask any finance professor, what are you working on? I'm trying to solve this endogeneity issue in my corporate finance research. So that's fourth assumption. As long as you have exogeneity, okay, mean, zero conditional mean of error terms, you're fine, okay? Fifth assumption is homoscedasticity, okay? What? So long. Homoscedasticity. Homo means same. Skedasticity means like spread it out. Same degree of spreading out. What is spread out? Those residuals. Okay, spreading with respect to what? With respect to your regression line. You see this picture over here, okay? Your regression line must be something, over there, right? And then the idea is that the spreading, okay, spreading has to be equal degree. Picture over here on the right-hand side is much more precise in that sense. Let me erase this part. and then you see at each given point of x1 value, okay, x1 value, you throw a perpendicular line and you measure the distribution, okay, estimate the distribution of your residuals, right, residuals. Then what should you see? The variance of this, okay, should be the same. Should be the same variance. That's why you have sigma squared, sigma squared, sigma squared, all the way down 3. Okay, it's the same sigma squared. Okay, it does not have any subscript, right? I never said sigma 1 squared, sigma 2 squared, sigma 3 squared. I said sigma squared, which means the same all across. That's something called homoscedasticity. Okay, we need that assumption. Otherwise, your estimate will be biased. That situation is called heteroskedasticity. You see much more spreading out, okay, as x increases, or vice versa, okay. The variance of this residuals matters a lot. We want it to be homoscedastic, right? Same all the way down. As long as you have these 5 assumptions holding, and you have a goal called Gauss-Markov theorem. Gauss-Markov theorem. When the 5 assumptions hold, OLS estimator beta hat is the best linear unbiased estimator, blue, right? BLUE, best linear unbiased estimator. Okay? Best means what? Minimum standard error of beta. You want to have some precise estimate of beta, the slope coefficient. Let's say slope coefficient is 2. How much are you sure? How precise is that estimate? That depends on the standard error. The smaller standard error, the more precision you have, the more precise you are, the more confident you are about the beta being 2 instead of 1, right? You need 5 assumptions over there, right? As long as you have these 5 assumptions, then you don't need to go for other competing estimators. So that's the Gauss-Markov theorem, right? By the way, what do you mean unbiased estimator? Well, it means that average of your beta estimate should be true beta, right? What beta hat, right? For example, your CAPM characteristic line, right? Characteristic line for, let's say, Tesla, right? You have, what is it? Tesla's return, okay? And then market return over here. And you ran a market regression, market model regression like this. And you have this slope term, which is beta hat, okay? What is Tesla's true beta? Isn't that this beta hat? And the answer is not really. Not really. We just estimated once, right? And it's always an estimation with error. We don't know the true beta. You cannot observe. 관찰 불가능해요, right? In Korean terminology. You cannot observe true beta of Tesla. We are just estimating with some errors. But Gauss-Markov theorem says as long as you have those 5 assumptions being holding, then your OLS regression, okay, is blue, best linear unbiased estimator. So much so that as you estimate beta hat time and time again, okay, average of your beta hat, okay, will be your true parameter beta, true beta. Okay, so that's the idea of unbiased estimation, and then the blue, best unbiased estimator, linear unbiased estimator, right? Gauss-Markov theorem. Okay, very important. So make sure you have it in your mind, right? More precise proof of this thing is something you're going to learn in econometrics class, perhaps in more advanced undergraduate or master's level class. So go ahead and enjoy that class. I'm not going to ask you about proving stuff, but those assumptions I can ask you, right, in your exams. So be prepared, right? Another assumption of classical linear regression I want to point out is non-autocorrelation of the disturbances. What do you mean? The disturbance means the epsilon part, the residuals, right? Epsilon, I, and T. The thing is, for example, autocorrelation means like the residual or any variable is correlated with its past values. So this guy, E of time t, epsilon I of t, being correlated with epsilon time t minus 1. Okay? Yesterday's epsilon and today's epsilon, if they are correlated, then we say they are autocorrelated. How about time t minus 2 all the way down to t minus m or n? Yeah, if they are correlated, then you have autocorrelation problem, right? But that correlation, autocorrelation, will screw up your estimation process. So we want it to be non-autocorrelated, to have clear linear, regression, okay? But Gauss Markov theorem, it doesn't specify that this assumption has to hold, but the previous 5 yeah, you have to make sure about it. Anyway, linear models, yes. Many problems in big data involve a response of interest y, or the variables that you are interested in, those dependent variable y, and a set of covariates x to be used for prediction. A general tactic is to deal in averages and lines. Regression to the mean, regression to the averages, and then the lines. We will model the conditional mean for y given x. It's always going to be a conditional mean, right? 조건부, right? 조건부, right? Conditional. You have to be given for x variable, your explanatory variable has to be given. Once it is given, what is the average of your dependent variable, right? It could be any functional form, but in linear regression, we hope it to be linear combination. Beta times x plus another beta times x plus beta times x, blah, blah, blah. X should be what? A set of vector, right? I mean, x should be a set of vectors, right? Set of vectors. Actually, x, this guy has to be a big matrix. Okay, matrix. The first, okay, of your vector has to be one vector. 1, 1, 1, 1, 1, 1, 1, 1. You have to have this in your mind. I mean, I'm going to show you in the next slide. But all your observations, right? Sample observation 1, 2, 3, 4. First person, second person, third person. Or first company, second company, third company, all the way down to n companies, right? You have n company sample, okay? And then that's the row number. And then your vector has to have this n element in it, okay? Vector, column vector, okay? The first column vector, we always start with a constant 1, right? That does not change, right? It does not change. There must be some level. The dependent variable does not change, so let's model it with 1. That's the idea over here. 1, 1, 1, 1, 1, 1, 1, 1. Okay? And then x1, x2, x3, x all the way down to p. Why is it sub p? Well, this is because it's a parameter, right? We're going to estimate the beta parameter. So we are saying some subscript p over there. Don't get confused. So it's going to be n by what? P plus 1 matrix, 행렬, right? N rows and then P plus 1 columns over there, right? Like that. So first column will be 1, second column x1, third column x2, all the way down to P plus 1th column, which is x sub P, right? And then with this, you have beta coefficient for all respective vectors, right? Those beta, this is a vector itself, right? It's a vector itself, and then those elements should be scalars. Elements should be scalars. Beta 0, beta 1, beta 2, beta all the way down to beta p are the corresponding coefficients. The products should be x product of beta, or x times beta. I would say x times beta, like this. Yeah, if it is just a scalar multiple, we just say x beta or dot x dot beta. But this is a matrix times a vector, so we say this mark over here, so that it's going to be beta 0 plus, which is what? Beta 0 times 1. Okay, first column vector times the coefficient of this column vector 1, beta 0. That turns out to be just a what? Intercept, y-intercept. Okay, and then the next one should be multiplication between these two, x1 and beta 1. And then the second one, x2 beta 2, all the way down to xp beta p, right? Like this. Okay. The notational convenience, we use x0 equals 1 for the intercept. Yeah, this is just what I already said. The first element over here, right? It should be 1. X, big X, right? Prime beta is a vector multiplication of a matrix, right? The number of observation is n, and the number of parameter is p, actually p plus 1. As I said before, we have a constant beta 0, so p plus 1 should be there. Now, X is a n, n by p plus 1 matrix, so n rows, p plus 1, right? And then beta is a vector with p plus 1 elements over there. It's a column vector beta 1, beta, as you see on this equation over here. Holy cow, you may say. No, it's okay. It's just a matrix. Big X, right? What is that? Well, n observations, as I said before. The first column vector is a constant. That does not change, right? I just set it as 1. It could be like 1,000, 1,000, 1,000, 1,000, 1,000, but, well, as to the extent the number, any scalar does not change, why don't we just use it as 1? Okay, it's a very simple number, but not 0, because 0 nullifies everything, so it screws up your estimation. So 1, 1, 1, 1, 1, 1, 1, 1. Okay, that's the first column, and it's going to be our intercept. In CAPM regression, it's like alpha kind of concept over there, which is constant, which is a intercept. And then the second column is the first variable. As I said before, this may be your leverage ratio, x1, 1, right? Always the index, the subscript over here, right? The order is what? The row, column, row, column, row, column, right? First row, first column, 1, 1, right? So that's why if you go down the list, the final one is x sub n1, which is like nth row, first column, right? Leverage ratio of nth company. You can think of it that way. Okay. And then you have p variables on your matrix. For example, x1p should be your profitability of company 1, okay? ROE of company 1 on this over here, right? And then move down the list and you'll see company N's ROE over here, okay? So that's this matrix. And then the vector that you're going to multiply has beta 0, beta 1, beta 2, blah, 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 beta P, like this. So if you do the multiplication, it will be like the first one, 1 times this guy, that's that guy. The second one times that guy should be that guy. And then the last one times that guy should be that guy, right? So first row, okay, first row, first row, last row, last row. So it's going to be n different observations when that corresponds to y1 all the way down to yn. And we're going to call this y1 through n as a column vector y, right? Nice notation. Arrow or this direction? Yeah. Okay, so it means y1 should be like this, right? With some error epsilon plus epsilon 1. Okay, but just we omitted it, right? And then we should write y should be big X times beta, right? Like this, just to be precise. But for convenience, mathematicians, after a certain while, they write it as X prime beta, okay? There's no prime over here, no, just delete it. X prime beta, as you saw before in your previous slide, okay, in your previous slide. So don't get confused. That's all that I'm trying to say. And then familiarize yourself with mathematical notations, right? So this guy will come up every now and then. And then marginal and conditional distributions. Those are some concepts that you want to distinguish, right? On the left, you see a frequency, the histogram of home values, and then as a whole, right? As a whole. And this is something called marginal mean. The precise definition of it, we're going to talk about it in the next slide. But this is roughly the marginal mean concept, the mean that we understand it roughly, okay? But what is interesting is the conditional mean. Conditional mean, what the heck is that? On your right-hand side, what do you see? Well, not all homes are the same. Some homes have bathrooms. Some homes does not have bathrooms. Not only that, some homes have many bathrooms, 목욕탕 in their house, right? And then the home values should be dependent on, maybe the home values may be different on average depending on the number of bathrooms that you have. Okay? No bathrooms, well, the cheapest price, I guess. And the biggest number of bathrooms, mansion. It's like luxury goods, right? So it will be very expensive. So let's see on the horizontal axis, the number of bathrooms, 0. Oh my God. 1, 2. Okay, fine. And then the 3, 4. That's quite getting luxury. And then 5, 6, 7. Oh my God! Why do you need 7 bathrooms? And then there are some, houses that have this many number of bathrooms over there. Like it's gonna be like Michael Jackson's home or something. All right. So the home value, depending on that, you see a box plot, right? That tells us about the median and interquartile ranges of those home values depending on the number of bathrooms, and it increases, right? The whiskers tells us about the 1.5 times the the interquartile ranges, and then those circles shows us the extreme values, extreme in the maximum value, home values over there. Okay, and you can also see that some homes that has only 1 bathrooms, they have extreme home price all over the top over there, right? Which is no different from the home values extreme in the number of 7 bathroom house, right? Why is that the case? Maybe this small house in Manhattan, maybe, okay, in the 5th Avenue. Yeah, of course, it can be very expensive. Anyway, so that's what's this? This is conditional mean, right? Something called conditional mean. Conditional mean is a function that depends on covariates, other variables, right? The data is distributed randomly around these means, right? So we need to have some kind of distinction between these two. Conditional means versus marginal means, okay? To be more precise, the marginal means is the weighted average of the conditional means with weights equal to the probability of being in the subgroup determined by the corresponding value of the conditioning variable. So population consisting of N1 men and N2 women. The size of entire population will be big N, which is N1 plus N2. And Y, let's say this is a height. And X is, let's say, a gender. Conditional mean of these, conditional mean of the height of people, okay? On condition that the person is male versus the person is female, the average height will be different. That's conditional mean height. So that's what you see. Expected value of Y given male versus given female. And the first one is the sum of all men's height divided by number of men. And the second one is the sum of all women's height divided by the number of women. So that's conditional means. Good. That's easy. The second page, you see it. Marginal means, right, will be defined like this. Sum of all heights divided by the total number of observations. Yeah, that's the mean that we talk about, right? But we analyze it in this way so that the numerator should be sum of all men's height plus sum of all women's height, split it, and then you have N1 and N2 showing up. And then the denominator has N1 plus N2, right? So, and then the numerator, you still have what? Conditional mean of mean height of male and female, right? Now you can split it so that this guy, N1 over N1 plus N2 should be the weight of male, and the second one would be weight of female, right? The weighted average of conditional means is something called marginal means, right? So that's one thing that we want to distinguish. Now, in a Gaussian linear regressions, right, Y given X should have a normal distribution at whose mean should be your predicted value, X beta, right? X times beta showing up again. That's mean, what we call mu, right? And then standard deviation order, standard deviation being sigma, right? So that's Gaussian distribution, linear regression. Conditional mean should be expected value of Y given X should be X prime beta, this guy. Okay? And with just one X, big X, which is one variable, univariate regression, we have simple linear regression like this. Yeah, Y and X, and then 1 to 2. X increases from 1 to 2, and you see the line estimation to be Y equals alpha plus X beta. That intercept alpha should be this guy, and then the slope is, which is the rise over run. Okay, rise over run. That's this guy. The coefficient used to be on the left hand side over here. Okay, yeah, should be the same, right? Expected value of Y increases by beta for every unit increase in X. That's the relation that we can infer from this regression, after all. Good. Now, the next page. Yeah. Today's lecture, I'm going to focus much more on the slides, and I'm going to give you the data called orange juice, or OJ. And then you're going to play with those code yourself at your home. Okay. Here I'm going to, in the interest of time, I'm going to discuss the slides first. And the next week I'm going to talk a little more about the code itself. Right. So orange juice, right, is the data that the textbook author provided. Okay, OJ, yeah, OJ, not OJ Simpson, by the way, but OJ. Three brands they have, right? One is Tropicana, okay, orangey, tok tok tok, Tropicana, orangey, tok tok tok, Tropicana, yeah. Somebody should shut my mouth, right? I know. Minute Maid is the second one, and then the third one is Dominique's, right? And then there are 83 Chicagoland stores. They gather the data from here, demographic information for each price, sales, log units moved, and log units moved. So it's a number of units moved out, okay, sales quantity, and whether they're advertised or not. The variable is called feature, okay, featured advertisement versus not. It's going to be a 0 versus 1. And then data should be on oj.csv. Code should be over there with you. Now you will be able to draw some kind of box plots like this or scatter plots like that. The box plot of log of price, right? Depending on the brand name, okay? And then log of sales quantity, like log of move, against the log of price, right? You see what is it? As the price increases, less of a sales quantity, and a cheaper price, more sales quantity. The relation goes on, right? Inverse relation, demand kind of relation. You can see it. Each brand occupies a well-defined price range. You see that? You see that? Green color, which is Dominique's, right? Seems like what? The average price is a bit cheaper, whereas the Tropicana, tok, right? That's kind of more expensive, seems like. Is that what's going on? Yeah. Over here and over there. And the price range, right? You can see it. And not only that, as price moves, as price moves from here to there, how does the sales quantity move from there to here, right? Those here, I'm going to say it, the elasticity, okay, elasticity. Price elasticity may be different, okay? Why would they be different, right? We're going to talk about that, right? Taking log, right? Every now and then, by the way, when you take run regressions, you will face this problem of taking the log of the variable. Why? Okay? This would be a frequently asked questions in your job interviews or master's degree or PhD degree interviews anyway. So you have to be familiar with this one. Why do you take log? Log of price, log of quantity, or whatever. Okay? There are several reasons why you do it. Okay? First of all, positive skewness. Positive skewness. You want to have it some bell-curved, symmetric distribution to have your OLS regression going fine. If it is positively skewed, right, those estimates will be driven by extremes, so that your estimation will be biased. Now, log linear, okay, regression is also there, right? That the positive skewness is not the only reason you take the log, okay? There are some situations when you have to take log. Log linear, you're going to talk about it in the next slide. When you assume some kind of multiplicative relationships among variables, then you can take log for dependent variable, okay? Yeah, the positive skewness is not necessarily for the dependent variable. It is much more for both the dependent variable and the explanatory variables, right? It could be both or any of these. But log linear is about the dependent variable. Log is about taking log of both dependent variable and your explanatory variable. We want to estimate the elasticity, okay, elasticity. What the heck is that elasticity? We're going to just wait for that a little bit. Yeah, so get ready for that. This one picture over here is talking about the skewness when making a linear point. Okay, this goes up, that goes down. Okay, think about the scale on which you expect find the linearity. Okay, linearity. So, for example, the relationship between the imports and GDP, right? How much you import, and then how much does that is that correlated with your GDP, right? The more imports, it seems like the more GDP, that bigger the economic size in your country, right? Of course, it's all about the size of the economy, okay? I'm not claiming causality here. Does that more import cause your country to grow faster, or your economic size of your country grow bigger? Does that import cause it? I'm not saying that. I'm agnostic about that. Okay, I'm just showing you the correlation, association. Okay, but the left picture is kind of screwy. What do you mean? The United States far above there, and then India and Japan, and then the rest of the countries are concentrated way down there. What? Why is that thing happening? Because the country's GDP size and import size is highly positively skewed. Okay, you see positive extreme value called United States. The rest of the countries are clustered in the downside over there, 300 different countries, right? So this one picture does not tell us much about any relation, the linear relation between these two variables. So why don't we take log of both dependent variable and explanatory variable, x variable and y variable, y and x variable, right? Both take the log of it, and then now we have more, more intuitive picture, right? Positive linear relation, we find it so that we may be able to run some linear regression based on it. Okay, the left hand side, we don't know what the heck on that cluster. The black side over there, is it more like a quadratic relation or three cubic relation or sine cosine relation? We don't know, but as we take the log, we can safely say, oh, it's linear. Okay, we can run some OLS regression based on these two variables. So if your scatter plot looks like the left hand panel, consider using log, the first point, skewness. All right, now log linear. We often model the mean for log of y instead of y, dependent variable. Why? Okay. Multiplicative relation is assumed over there in that case. What the heck? Multiplication relation over there. So let's see over here. The second line, log of y should be equal to log of a plus beta 1, x1, beta 2, x2. Let's simply assume three items. The first item is the constant item. The second item and third items is just the two variables. Let's say the leverage ratio and profitability, just like before, right? Two variables. The constant term, why don't you say beta 0? Well, just for, you wait for this and you can see it, right? Log of a instead of just beta 0. It's just a constant anyway, but let's wait. Now, what do you see? You see the log relation. By the way, from now on, you are no different from engineering guys. You are Iqua guys. So engineering guys. Iqua guys play with natural log E. That's why they're called Iqua or engineering guys. Natural log E. And then that means your log, L-O-G, okay, should be ln. What you usually learned as natural log, right? ln, okay? I'm going to call it log like this. I know some of you have learned log, okay, base 10 in your high school math. Log base 10, you used it, you wrote it just as log, and then log base natural log e, okay, log base natural log e, you used ln sign, okay. Perhaps in your CPA exam you may have used this one, but I say screw it. Everything is natural, okay. We are engineering guys, 이과 guys, no different. So you have to use log, which will be equivalent to ln, right? Make it your habit. From now on, log should be natural log. Log base 10, forget it. Okay, 잊어라, right? 어렸을 때, like 올챙이 시절, like okay. Yeah, so that's what's going to happen over here. Then what do you see? Well, the rule of log, right? You remember that? This one, okay? You can understand it, okay, analyze it, or understand it, interpret it as log of e to the power of beta 1 x1. That's because log of e to the power of a is a. Make sense? So whatever a is there, bring it up to the exponent of natural log and the natural log over here. E, right? E, the exponent of e and then the natural log, right, over here. So that's what's going on over here for this guy. How about this guy? Do the same, all right? So what do? Well, you have log, 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 all based in e, natural log. Fine. What do you want, Andy? Well, I want you to combine this guy because there's a log property that says your pluses will be multiplication. Okay, log of a times e to the power of beta 1 x1 times e to the power of x2 b2 beta 2, the whole thing, right? So that's what's going on over here. As it turns out, a times, right, e to the power of beta 1 x1 times this guy should be just a summation. Okay, multiplication becomes a summation. That's the magic of e or the exponent. All these kind of things, right? Multiplication becomes summation, vice versa. Okay, so you have this relation, and remember this was about log of y, right? That tells us that y should be equal to a times e to the power of beta 1 x1 plus beta 2 x2, which is multiplication of these things, right? So I said once you take log of y, you are assuming some kind of multiplicative relation between these two variables instead of additive relation. Additive means like a 더하기 관계, versus here is like a 곱하기 관계, 곱셈 관계. All right. So predicted y is multiplied by e to the power of beta after a unit increase in x. Recall that log of y is 0, and that is what? E to the power of z. 지수는 로그 및 진수 in Korean memorization, right? 지수는 로그 및 진수. So your base mit was e, right? So that's e over here, over there. 지수는 로그 및 진수. And that e is like what? 2.71282828, right? Okay, fine. Now log of a times b, yeah, you see this relation over here. It's going to come back again, right? So Make sure you memorize. Keep your hands busy, writing like crazy. Yeah, that's the only way you can adapt and then survive. And it's actually fun, right? Good for killing times, anyway. Anyway, we use log ln. Yeah, I told you about this. Yeah, whenever we need log base 2 or base 10, I'm going to, the R, right? R says log 2, log 10 for base 2 or 10. Yeah. And then whenever y changes on a percentage scale, use log of y prices. Foreclosed homes sell at 20% to 30% discount sales. Our year-over-year sales are up 20% across models. Then use log, right? Remember the domain of log function is always positive, right? The log function, remember? Y equals log of x. Remember this? So here is the graph, y, x, and then the log function should be like this. And this is 0. The domain has to be positive area over here. That was log function, right? Volatility. So you can take the log of some positive numbers, okay? As long as your variable is positive, okay, non-zero positive, you can safely take log, especially when it is very positively skewed, okay? Whatever extreme value you have it, okay? Log function brings it to non-extreme values. Extreme values, you may have it, but log function brings it to very low variables, so that the highly skewed distribution becomes more like a bell curve later on, right? Volatility or failures or rainfalls, most of the things that are strictly positive, failures, you failed or not, that kind of things. How many times you failed, right? You never fail minus times, right? Rainfall, right? You have positive number of rainfalls, right? Instead of minus number of rainfalls. Yeah. So that's that. Sensitivity versus elasticity is the next thing you have to think about, okay? What was that about? Well, price elasticity in your microeconomics 101, right? Your staple goods, right? Rice, wheat, all these kind of things. You have to consume it no matter what, right? Even if the price is extremely high, you have to consume it because you have to survive. That's price sensitivity, elasticity. Come on, elasticity. What are you doing, Andy? Right. Elasticity. Small elasticity. Inelastic. Rice, those staple goods, inelastic. Luxury goods, very elastic. Okay? But the elasticity itself is about the percentage change with respect to the percentage change of your explanatory variable. Percentage change versus what? Well, sensitivity, right? Sensitivity. Let's start from sensitivity and then we'll move down to elasticity. So sensitivity was about what? Delta y over delta x. So y variable, x variable, delta y over delta x, rise over run kind of issue, right? Kyulgi kind of things. Sensitivity of y with respect to x, we call it this way. And how much does y change when x changes by 1 unit? Okay, that was it, sensitivity, right? Your characteristic regression, your kappa and beta, is it sensitivity or elasticity? Have I ever asked you about, Tesla is more elastic to S&P 500's changes, index return changes? Did I have I ever said elasticity? No, I've never said that, right? I always said what? Sensitivity, right? Sensitively moving with respect to market. Okay? That's sensitivity that we are talking about over here, right? Now, having said that, what's the elasticity? Well, that is more complicated. What? You have this. Your numerator is not delta y, but delta y over y. Ah. And then your denominator has what? Not delta x, but delta x over x. Ooh, more complicated. And this is why the proportionate change of y, okay, the proportionate change of y is on your numerator, and then the proportionate change of your x is in the denominator. Make sense? Instead of the change itself, you have proportional change, the percentage change as numerator and denominator. That's what we call elasticity, right? That's what we call elasticity. What the heck? What is the difference? What percentage does y change as x changes by 1 percentage point? This is addressing that question, right? This is addressing that question. Didn't you say 1 percentage? No, previously in sensitivity, we said 1 unit, whereas over here, 1 percentage point. Okay, that's elasticity. Good. Okay, so let's say, yeah, elasticity is beta. Okay. Then what happens? Well, let's do the math. This is arithmetic, and it goes back to your calculus. 이과 수학 a little bit, right? Or engineering math, basic calculus, by the way. So you should familiarize this one, right? Okay, so let's do the math. The numerator and denominator. Keep the numerator on your left-hand side, and then the denominator, bring it to your right-hand side. This happens. Make sense? Good. Then what? Well, this delta is actually if you shrink down the delta, right, the difference very small, and it goes to your differentiation concept, right, 미분 concept, so that delta x you can label it as dx. In any case, they were meaning the same thing, right? Greek delta means d, differentiation, right? So let's switch this delta into d, right? And the left-hand side, you have dy over y. And then right-hand side, you have beta times dx over x. Good? That's good. Fine. Okay. Now, take the integral of both sides. You may say, are you crazy? What? I haven't learned that. Well, in your calculus 1 or 2, in your the college calculus, you must have learned it. But this is a refresher if you learned it, or if you haven't learned it, learn it right now, okay? You can take integral of both sides, right? As long as you have d on both sides, okay? We are just integrating with respect to different variables over here. But you have to be just consistent, right? Integral with respect to y on the left-hand side, integral with respect to x on your right-hand side. And what do you have? Well, integral sign. Ooh, over here, hello. And then you see this will be what? Beta times integral of 1 over x dx, right? This guy, this ugly term is nothing but dx over x. That is dx times 1 over x. It's the same thing, right? Now, what am I trying to do over here? And you know, integral of 1 over y should be log of y. What? What? Again, this is engineering math, right? Basic engineering math, by the way. This one holds. There, it is involving something called implicit differentiation process, okay? Implicit differentiation, that's something you can Google search it, and the Wikipedia, all those things tells you about it, right? Anyway, you can do this because differentiation of log of y, okay, log of y differentiated with respect to y should be 1 over y, okay? Don't lose thread, okay? 정신줄 놓지 마시고, right? Catch it. Just hold on to this one, okay? Wait for the next slide, okay? Here, so let's say this, then, we did that, right? So we did this on this part, right? So log of y should be what? Log of y should be beta times log of x. What? How come that happens? Well, this one, right, becomes this. Because the left-hand side, you integrate 1 over y, that will be log of y. On your right-hand side, you have beta times the whole integral ugly term, that is nothing but log of x. Okay. Then what? This means that if you regress log of y on log of x, the coefficient should be beta, which is the elasticity that we talked about before. Over here. Right? It's kind of involved math for some of you, most of you, I guess, but this is it, right? Elasticity. Is there any way I can skip it and then just master everything? No. This is the separator. This is the hurdle that you have to get over. So take it. Bite the bullet, please. That's it. Price elasticity, a simple orange juice, right? Elasticity model for sales y has like this. Expected value of log of y should be gamma times log of price plus other covariates times beta coefficients. Elasticities and log-log relation. For small values, we can interpret gamma as percentage change in y per 1% increase in price. This is elasticity, not sensitivity, right? Yeah, we run this in R, okay? How do we do that? Well, log move. In your regression, you will have a sales. So you have to go like a log of sales, log parenthesis sales, tilde. Tilde means like kobrang, right? Tilde. Log of price plus brand, and then data specified as OJ. Everything in parentheses, GLM, generalized least squares model. And then the result will spit out like this. Intercept, log of price and its coefficient, and then the brand Minute Maid, and then brand Tropicana. Okay? Those coefficients are shown over here. Intercept, and then the other coefficients. And see, sales drop by about 3.1%. I'm sorry, 3.1%. This guy. For every 1% increase in price. Okay? So that's price elasticity of orange juice. And then the regression in R, you need only one command. Regress. R is G, should be GLM, and then parentheses everything, and then comma specifying your data. Now GLM, I told you about this. LM works too, but GLM does more. And then Y tilde A plus B is the formula that defines your regression. I want you to regress Y variable on A and B only. But what if I want to regress Y on the other whole variables, right? Just forget it and just throw everything and run a regression and tell me. That's Y tilde. Regress on every variables in my data except Y. Yeah. The object regression is a list of useful things. Yeah. and then summary regression or summary reg, right? Then by this regression, you are creating a matrix called REG. So you want to get the idea of this matrix. The command should be summary REG. And it prints out a bunch of information. And there you have some coefficients, right, of your regression results. And parenthesis reg gives the coefficients. Predict reg, comma, new data equals some new data set names. Well, it gives you predicted values. Predicted value, what is that? The values on the regression line or the hyperplane. Okay. My new data must be a data frame with exactly the same format as my data. Same variable, same names, same factor levels, and blah, blah, blah. And then design matrix is something you want to make sure this time. What happens to brand Dominics or make Dodge kind of things? It's like a categorical variable, okay? Previously we had cars, trucks, makers, Dodge, GM kind of things, okay? Here you have Tropicana and then the other Dominics kind of things, right? Categorical variable. We want to create a dummy variable that is 1 if the observation belongs to Tropicana and 0 otherwise. You want to also create a dummy variable that is 1 if it is like what is that? The other one. Yeah, Dominique, let's say, and then the other 0 otherwise. The same thing, right? Maker of the trucks, Ford versus GM. You want to create GM dummy variables and then Ford dummy variables. How do we do that? Well, R does that kind of automatically. The regression formulas look like this, but brand is not a number, so you cannot do brand times beta. The first step of GLM is to create a numeric design matrix. Okay, I'm not going to ask you to how to construct a design matrix yourself, but here's the idea. It's just throwing out a dummy variable automatically for you. Convenient. That's the whole idea. It does this switch called to the model matrix function, right? Make GMC Ford Dodge Ford in each different variables, right? Intercept will be 1 1 1 1 1. Constant term, and then the make Ford will be created and make GMC will be created with this design matrix kind of function. Okay, so that GMC, right, GMC, that dummy variable, okay, will be 1, okay, for the first observation over here because it is GMC maker, and then the second observation, the GMC dummy variable will be 0 0 0, right? Because they are Ford, Dodge, and Ford. And make Ford dummy variable, that's 1 1 for the second and fourth observations and 0 otherwise. Likewise, automatically creates this dummy variables for you. The factor variable is on the left, and on the right we have numeric x that can multiply against beta coefficients. Okay, fine. Now, all these dummy variables, right? By the way, all these dummy variables will serve as kind of another intercept, added intercept, shall I say? Okay. So Ford, that subsample of Ford will have their own the coefficient, the intercept, and then the make GMC, they will have another intercept of y. Okay, in addition to the common intercept that you have, right? So get ready for that discussion later. Okay, parallel line, you can think about it that way. Our OJ GLM uses model.matrix to build a 4-column design. X should be model.matrix, and then should be log of price plus brand and data OJ. Then let's see the first observation. If you run that command, you will see this kind of first observation showing up. The first one is intercept, okay, in this matrix called X. design matrix. You say, I told you before, this starts with the intercept, which is 1, 1, 1, 1, 1, 1, 1. And then it also sticks in log of price over here, because I said log of price should be the first column, the second column. Yeah. The remaining column should be based on the brand, the categorical character variable or categorical text variable. We create a dummy variable for each unique text string. Okay, so Minute Maid, okay, Minute Maid and Tropicana, right? That dummy variable is created. The first observation is from Tropicana. That's why we did 1 over here and 0 over there. Each vector's reference level is absorbed by the intercept. Coefficients are changed relative to reference. Dominic's here to check the reference level of your factors. 2 levels. My factor, the first level is reference. What do you mean? The reference variable, the default, right? The default. When you do dummy variable regression here, when you do the dummy variable regression, we have to be careful about multi-collinearity. What the heck do you mean? Well, here, based on brand, 3 brands we have. One is Tropicana. I would say dummy variable 1, Tropicana. I should. Dummy variable 1. And then another is dummy variable for Minute Maid, I should say. And then the third category is actually Dominique, right? Dominique. If we create a dummy variable for Dominique, right? Then what happens? Well, all the observations in our data set belongs to either one of these. Okay? There will be no case that doesn't belong to any of the brand. There's no brand, no such thing as no brand orange juice in our data set. Okay? Any of the 3 completes our data set. So, what's the problem over there? If we throw in all these dummy variables of brands, 3 altogether, with this intercept, which is 1, 1, 1, 1, 1 all the way down, what happens? Well, this 1 matrix is nothing but the summation of all 3 dummy variables. Aha! That's precisely what we worried about before, called multi-collinearity. This one is a linear combination of the remaining 3. You are in trouble. You will be screwed. Your regression will not work, right? So that's why we want to omit one of this category, okay? That will be something called the reference, right? Reference, or I usually call it default, right? What's the default? Well, here Dominique is a default. So we just omitted, and then the observations will be 0. So that those 3 linear combination will not be 1, okay? So that's the concept over here that I'm trying to say. To check the reference level, blah, 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 go ahead and do it. Okay, fine. Yeah, that's it. And then the next one, interaction. Okay, 교호작용, we call it 교호작용. What do you mean, right? 교호작용 in Korean terminology. 2 variables, right? Interacting, and then the interaction, the chemistry, creates another influence to the dependent variable. Okay? In the default, the bankruptcy prediction model, I set leverage and then profitability. Okay? What if there is interaction effect between these 2, leverage and profitability? So for example, highly levered company, yeah, it's going to hit more bankruptcy, but if it is more profitable, then would it still be having higher bankruptcy, or would there be a reduced probability of bankruptcy? Because it's more profitable, you can borrow more. The profitability itself combined with this leverage, how does that affect the bankruptcy chances? We don't know. Okay, the combined effect. Okay, so that kind of combined effect, we can capture it using interaction term over here. Okay, quite often used in the regressions, as you know. Beyond the additive effects, variables can change how others act on y. An interaction term is the product of the two covariates. So your expected value of y given x should be a linear combination of other variables, and then xj and xk. Those two variables we are interested in, and then we introduce this interaction term over here, xj times xk. Throw it into that regression, and there we will have a third coefficient, beta jk. All right? Then, how can you interpret the result once you estimate these betas, right? How can you interpret the result? Well, the way I usually do it is just pick one variable. For example, over here, xj. Okay, a common variable xj. It could be xk, but take it from the perspective of xj, and then gather together like terms, 인수분해 kind of things. Gather together like terms. You have xj over here and over there. So parenthesis, beta j is over here, and then beta jk times xk should come over here. Now you see the coefficient of xj is not just beta j, the plus beta jk times xk should be your total coefficient over here. Okay, your interaction effect comes in over here. Usually in this setting, we take this guy, xk. Usually we work with a dummy variable. Let's say Tropicana dummy over here. Okay? Why dummy variable? Because it makes our calculation very easy. Because this dummy variable will be either 1 or 0. Tropicana 1, otherwise 0. So if the brand is Tropicana, you have 1. Okay, 1 over here, and that multiplied by beta jk, so it will be beta jk itself plus beta j. So your coefficient when it is Tropicana, it will be beta j plus beta jk. That's Tropicana. Okay? If it is not Tropicana, okay, it's 0. So that it's going to be 0, canceling everything here. All you have is beta j. So your interpretation is easy, either this or that. So make sure you work with dummy variable when you use interaction terms. I also forget this part, so that I interact continuous variable with continuous variable, and my referees and other readers say, what are you doing over there, right? So make sure it is dummy variable over there. It makes your life a lot easier. Yeah, so that's that. So that the effect of EY, expected value of Y, of a unit increase in xj is beta j plus beta jk times xk. By the way, this one will be dummy variable, either 1 or 0, as I said before. It depends on xk. Yes. Interaction terms, very important, I told you. It makes your interpretation a lot richer, right? Analysis a lot better. Interactions play a massive role in statistical learning, and they are often central to social science and business questions, right? For example, right, you like compensation, like pays, right? CEO compensation, how much do they get paid, right? The thing is, billions and millions of dollars, right? 수백억 원. They get paid, right? But your payment, CEO payment should be sensitive to company performance. Better performing companies, better paying to the CEOs. Worst performing companies, no soup, no payment, right? 국물도 없어요, no soup, right? 국물도 없어요. 어디 페이를 먹으려고. So that's pay performance sensitivity. So strong governance. The company's CEO pay is much more sensitive to company performance, right? Interesting thing could be, well, male CEO versus female CEO, right? In which setting, which gender, the pay performance sensitivity is bigger, right? Could be a valid question. You can throw in an interaction term between company performance and gender of the CEO and see if there is some interaction effect, right? How about the race, right? Caucasian CEO versus non-Caucasian CEOs. In which case do we see more stronger pay for performance sensitivity, right? That kind of things. You can test it. Yeah. I'm going to give you some executive compensation data so that you will have some idea about how much they get paid. And you will see why I tell you don't go for CPA and try to become a CEO, okay, instead of CPA. CEO. Actually, those guys with CPA gets underpaid. That's why I say don't go there, right? But this is I'm just kidding. But this is a troubled time, recession. So going for CPA is no problem. Okay, it's your life anyway. So example number 2: do patients recover faster when taking a drug A? Okay, that kind of things. You can try it with interaction terms. How does advertisement affect price sensitivity, right? Or price elasticity? Okay, I should change that word into elasticity because you're going to see that here.